factor? Yeah. Did we still make partial fractions? Yeah. Did we still get rid of denominators by multiplying? Yeah. What was different? I would say this guy. What do you guys think? Was he a little different? Why did we write bx plus c over x squared plus 4 instead of the normal? Instead of what we have been doing with a single letter? What was different? Remember that big old table I didn't make you write down everything from? This one. Remember how we had two different options? We had both how to set up partials for linear functions and how to set up partials for quadratic functions? Or I should say factors. Are we okay to put just A, B, C, D, E, F, G over linear factors, whether or not they're raised to different powers or not? Yes. Why? Because that's the rule. That's how it works. Long story short, we're putting in the numerator an expression that is 1 degree less than the denominator. So the denominator has degrees of 1, then we put just constants above. But as soon as we have denominators with degrees of 2, what do we have to put above? 1 degree less than 2 is 1. We put above a linear expression. Like mx plus b, that's what bx plus c is. Now guys, they do the whole little subscript thingamabobber, and I don't like that. So I would have done this instead. Bx plus c here is great. Dx plus e, I don't know, that's a math number, maybe f. I use different letters instead, but either way, since we have quadratic factors in that last example we were looking at, we had to make an partial fraction. We had to make an appropriate partial fraction, but otherwise, aren't we just kind of doing our system? And our system says get rid of the denominators, which we did in this step, check, check. Distributed and canceled out appropriately, check, check. What was I just doing at the very end of class yesterday to show you that it's not that much different? Yeah, I was starting, well, first of all, I distributed everything out, right? And then I was looking at the like terms on one side and the other. So how would we go about finishing this puppy off? Someone give me an expression that has to be true. A plus B equals what? 3. How come? What terms are you using, Nathan? Awesome. Someone else besides Nathan? Although, good job. Give me another expression. Caleb, go.
4a equals 4. Oh, a equals 0.
A equals 1.
A equals 1.
Well, no, let me just, can I say your original? 4 equals 4. That's good. That's good. And then I have one more, but which terms were you using for that one, Caleb? Good. So we already used the purple. We already used the blue, and the last one, the last but not least one, is the green. 4x equals cx or c equals 4. If you guys want to know how those x's go away, check this out real fast. 4x had to come from cx. What can I do to both sides? So what do you end up with? 4 equals c. That's why we can just take the coefficients. Don't we love saving time if we can? Just take the coefficients, so 4 equals c. At this point, guys, it's just to put it all together and solve, right? Don't we already know C? What's A going to equal? Yeah. And then how am I going to find B? Plug it in, plug it in. So I have 1 plus B is equal to 3. Some of you are already mental math, just make sure you're not making mistakes. B is equal to 3. What do I do with all 3 of those? Plug them into the partial fraction that I was trying to complete right there, right? So then my final answer would be who over x? 1 over x plus who over x squared plus 4? 2x plus. Got it. Dun, 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 dun. It's for middle school, even though it's not for middle school, but it's usually for middle school. Anyway. That was complicated. Final answer, dun, 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 dun. Now, can we see one more tricky example? And I think this is technically the last one that I have. And if someone has something tricky from homework, feel free to grab it out. Maybe we can peek at one more. If anybody got stuck on any homework ones, maybe we can peek at one more. But hold on first, let's do one more. One more that I have ready for you. Write the partial fraction decomposition for actually need you guys to change something on these notes. You change distinct to repeated. It's accidental. Repeated. Why am I changing distinct to repeated? What's repeated? X squared plus 2 is repeated how? How do you see it? Do you see it? Yeah, it's been squared, so I have two different factors of x squared plus 2 in the denominator. Two different factors. Now, just a few of you, hold on, we need to ask ourselves a question though, right? Step number 1, we ask ourselves, is it improper?
No.
Careful. If you said yes, I totally understand why you said yes. You're looking here. But, what else do we have to consider? What else is in the denominator? It's squared. If we were to square x squared plus 2, now watch out. I'm teaching my Algebra 1 kids this today, how to square a binomial. You have to FOIL or memorize how to do it. In that you square the first, you square the last, and you double the first times the last, which will be 4x squared, right? That is how to square. What degree do we end up with in the bottom, long story short? A 4th degree, so is this improper after all? No, so be careful. Be careful. But now that we figured out it's not improper, we're supposed to just be going with our system, right guys? Alright, so step number 1. We factor, but the nice news is, isn't it already factored? Some of you are like, no, you can go further. Try it. X squared plus 2 is irreducible. It cannot factor any further. You can't do x plus root 2, x minus root 2, because that would be a minus inside. You can't do x plus root 2 squared. That should have an inner term. We're stuck. So we say, all right, fine. Partials. I'm making 2 partials because I have 2 factors. What's the denominator of the first one? You guys remember how to do repeated factors? Just x squared plus 2 to the first, and what would be my second partial fraction denominator? Got it. Just like we did with linear factors, you start to the first power, and then you build to whatever power you have. Yeah, if this was a cube, we would need to go ahead and, I'm just doing a what if real quick, guys. You would need to go ahead and make a next one, and then go all the way up to cube. Does that make sense? But we don't have a cube, so let's get rid of that. And there we go. What are my numerators going to be? AX good, AX plus, because it's a quadratic. So how about the next one? Isn't here quadratic also? Yeah. Now once again, you guys can do little subscripts if you would like. I kind of just like having very clear, distinct different letters. Alright, help out. Multiply both sides by the denominator. Let me do a quick plug for homework real fast. Kiddos, when we do stuff together in class, doesn't it almost always seem easier than when you're doing it by yourself at home? Just because it kind of makes sense in the moment when I'm talking you through and basically leading you to answers, doesn't mean you totally have it. You need to get home, you need to actually work on that homework. Get stuck, come in with questions. Maybe come in during math lab or lunchtime to ask or talk with a friend, say, hey, this is going on in PreCalc, what's going on? Have someone else explain it to you, have me explain it to you outside of class. All that needs to happen before a test, because if we just sit and say, it makes sense, PreCalc doesn't stick as good as Algebra 1 or 3 algebra, right? You gotta help it stick, and practicing is part of that. Let's come on back. Just letting you know, yes, there is a system, and yes, a lot of your classmates can quickly rattle off the system, but I need you to be able to rattle off the system and do it on your own, okay? What do I do once I multiply both sides? Oh, hey, what happens on the left? Cancel. On the right, stop, pause, no one answer, no one answer, no one answer. At the same time, when I count to 3, I want everyone to tell me what I'm doing when I use the rainbow. 1, 2, 3.
Distribute.
Okay, it's a little better. Thank you, my ones that answered when usually you say second. We'll keep working on it. We're distributing. On the left, the 8x cubed plus 13x remains. On the right, remember, these little guys need to go in parentheses. They're grouped. Ax plus b is being multiplied by, how many will be left?
1 x
Good,
squared.
because 1's going to cancel. I have just 1 x squared plus 2. Cx plus d is going to get grouped. How many are going to be left when you look at these two denominators? Yeah, they're all going to cancel out, so that's it. Now, what is one method of solving right now? Distribute and like terms. Use colors or use different shapes and make equations just like we just did. What's the other method? Strategic value. Let's review those real quick. Strategic values. 4x equals. Now, usually we like to plug in for strategic values zeros that we see in the parentheses. Now, the problem is only one of these sets of parentheses has only numbers. That's this one, right? Does he have any zeros that are real numbers? And some of you are like, I don't know how to think about that. Remember you set them equal to 0 and you solve and x squared equals negative 2, which, is this a problem if I have plus or minus square root of negative? Oh, that's imaginary. I'm looking for real zeros. Well, that doesn't work. So can we still use strategic values if we don't have any zeros or we don't have enough zeros? And the answer is yes. The answer is yes. Question. Couldn't we peek over here at his zeros? Does he have a 0 if you were to factor? Yeah, what would his 0 be? 0, that's 1. But technically, kiddos, strategic values, sometimes you can steal the values from the equation themselves, and sometimes you're like, whatever, let me just plug in some easy stuff to plug in. We can plug in 0, we can plug in 1. If you want to, we can plug in 2, or x equals negative 1. Not that you have to use this system or this method in homework, but it is kind of a nice method. It's like thumb trick, but it just can't be as short as thumb trick in these more complicated problems. Just to review real quick, strategic values, what do I do with that x equals 0 for the first one? Plug it in. Plugging it in where? Just to review real fast. Anywhere and everywhere there's an x. Kind of like f of x, and we plug in values for x, we're plugging in. So let's see if we can follow, okay? For x equals 0, we're going to have 8 times 0 cubed, which is a 0, plus 13 times 0. That's all 0. We're going to have a times 0 plus b times 0 squared plus 2 plus c times 0 plus d. Now, a lot of us don't want to write all that work because the left-hand side just ends up being 0. The right-hand side just ends up being b times 2 plus d. b times 2 plus d. Oh, bummer. Did that get us to an actual number? Does that let us solve for b or d? No. Alright, so here's a bit of a bummer with strategic values. Nope, it's not it. We can still use strategic values, but we might still end up with a nasty system. For instance, we could plug in x equals 1 and see if that helps at all. We're going to end up, long story short, 8 times 1 cubed plus 13 times 1. A times 1 plus b times 1 squared plus 2 is 3. Plus c times 1 plus d. And we end up with the expression 21 equals 3a plus 3b plus c plus d. Why is this looking really scary right about now? It has every single variable in the equation, in an expression. Could we keep going? Yes. Do you know how many x values we have to plug in if we're trying to solve for 4 different variables? Yeah, we have to do 4. To solve for 4 variables, we'll need 4 points, and then we'll have a system of how many equations? We'll have to solve a system of 4 equations. Here's my question. Can strategic values work? Yes, but are there times when it's like, you know what? This is getting way too complicated. I think it might have been easier to do what?
The other one.
Like terms.
That one.
So before we left this section, I wanted to really quickly at least remind you guys of the 2 different strategies. Sometimes strategic values is faster. It actually is what gets us to the thumb trick. But if you don't mind carefully multiplying polynomials, like terms can be a lot easier. For instance, if we were to rewrite this after distributing, we'd have 8x cubed plus, why am I writing 0x squared? That's weird. 13x plus 0 equals, if I was to distribute, I'd have ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. Now some of you a second ago were like, ew, I don't want to distribute all of this stuff, right? It seemed really messy, but maybe in comparison to having a 4-system equation, maybe it sounds a little bit better now. Because now how do we solve? Well, how many colors do I need, guys?
4.
4. I need to go find my x cubed terms, right? I need to go find my x squared terms. That's why I wrote 0x squared. I need to go find my x terms. And I need to go find my constants. Any quick questions about grouping like terms? Do we understand the idea? You're literally just trying to make equations from like terms on either side. So my equations that I would get, someone besides Nathan and Caleb and Ricky and Tyler. Ah, stop. Give me an equation, something I can say. I like it. 8 equals A. Keep going, someone else. What, Jason? Which one? Someone equals 0. I didn't hear what you said though. Yeah. Right? Check out the purple ones. A has to equal 8. Check out the green ones. 0 has to equal B. Keep going. Yeah, you can say 13x equals 2ax plus cx. What can we technically do since they all have x's though? Yeah, we can technically take away the x's. So you're right. From the x terms, we can say 13x using the blues. 13x is 2ax plus cx. But we can take away all the x's and just say 13 is equal to 2a plus c. One last person, help me out, the last one. Cheater, Caleb. 0 equals what? Someone steal it from him. Come on, David. Close, not B. Who are the other orange ones? Oh, D? Who else though? 2B plus D. Good, good, good. Look if that was you. Got it. Now, do we still have 4 equations? Yes. But are they impossible to solve? No, because I already see A. I already see B. Can't we plug in A to find C? 13 equals 2 times 8 is 16 plus C. C is equal to -3. And then what's D equal? We'll plug in B. 0 is equal to 2 times 0 is 0 plus D. D equals 0. That's a whole lot easier than that nasty system of 4 equations we were going to end up with right above. Alright. Thank you, my participants. All we have to do to finish off our equation is go ahead and come on back and plug and chug into our original partial fraction decomposition setup. Plug in A, plug in B, plug in C, plug in D, box it, you're done. Alright, I was gonna take a question from 7 for homework, but for sake of time, we gotta go 7-5. But the good news is we got a lot more people involved, and hopefully seeing those last two examples just kind of cements how to do partial fractions. There's always a system in place. You just have to, depending on what you have, sometimes long divide first if it's improper, and then sometimes set up a over or bx plus c over depending on what you have down in the denominators. Alright, what on earth do I think we can finish section 7.5 in 15 seconds? 15 seconds. Whoa! Minutes. 15 minutes. 15 minutes.
Exact same way you do systems.
Because.
But you use the n equals app on your calculator.
It makes it all shady.
Yeah.
The shady thing. Have we been doing shady things since algebra 1?
Oh yeah, but you can do it on your calculator.
You can check on your calculator.
No, you can graph it.
Don't worry, section 7.5. Some of this stuff you can do in your calculator. I totally agree. But you guys need to start writing. And I'm going to go get my calculator so that we are all on the same page as to how. But in algebra 1, you guys graphed inequalities of lines. Now we're going to graph not just linear inequalities, but possibly some other ones as well. Like the one you see down below, that's a parabola. More specifically, a parabola that's been shifted down one. But how do we graph inequalities? Well, we just graph it as though it was an equation. Pretend like it's an equals, and then we have to test one side or test the other. See if it satisfies, and if it does, you shade, and if it doesn't satisfy, you shade the other side. That's the mathematical, or I should say the algebraic way of solving and shading. But some of us have learned if it's greater than, you're almost always shading above, and if it's less than, you're almost always shading below. Remember how sometimes you have solid lines and sometimes you have dashed lines?
Yeah, dashed are when you have greater than.
Dash is when it cannot be on the line, so it cannot be equal to. Solid is when it can be equal to as well. All dependent on the inequality that you have at hand. You can do quite a few things with this. You can make pretty good graphs. I think I have my graphing calculator on ready to go. Oh, almost. Now, problem is, I have full confidence that you should be able to graph this graph without a graphing calculator. I'm just trying to demonstrate really quickly how you could use the graphing calculator to help. But before we use the graphing calculator, let's show off our smarts and say, wait a minute, it's a parabola that's been shifted. I already said this. Shifted how? Down. How many?
One.
Mm-hmm. So can't I just do a this and a this and a this and say swoop? Pretty close, right guys? If I want to be super precise, I could like plug in -1, plug in +1. They end up being the zeros of the function. So it could be a little more precise and say, hey, it connects like that. Why am I doing a solid graph? Well, because what's my inequality? Or equal to. It's not a line, but the same idea exists. We could always double check it with algebra if we want. For instance, asking ourselves, is the point 0, 0 a solution? Some of you might remember this from algebra 1, algebra 2. You would plug in 0, ask yourself, is that greater than or equal to 0 squared minus 1? Is 0 greater than or equal to -1? And the answer is true. And wherever the answers are true, that's where we shade.
Damn, that's the section. Let's go.
Right?
Homework time.
Pretty much. A couple things might get funny, but pretty much. Your graphing calculator, really quickly. How can you make it shade?
Turn the n equals app on.
Well, you could first of all just do it the old-fashioned way, which is have your little triangle shade up for greater than. Then you graph it, and it says, "Yay, let's shade up for greater than." If I can actually use the buttons. That's fun. The other way, which is the newer way on the newer calculators, is you could go to apps. You could type in alpha I for inequality. It'll jump to the i's. If you turn in inequals, now some of you might get annoyed by this inequals. It's under apps once again. Type alpha I, which is alpha, I don't know, x squared. All of a sudden you have these cool little like inequality things that you can do. We have to change this little thing back to our normal line. And then we can actually change our inequality, but you have to change it using the alpha button. So you could use alpha and then this last one. It's going to be greater than or equal to. Guys, look, it just turns on what you could have turned on. So I don't know if it's really that helpful. Whatever. And then you can go to graph.
What happens?
I find it's kind of, I don't know, gets in my way, but
No, but then you can. But the cool thing is that you can change the shading, so it just shows the
Just
intersection.
do it. If we accidentally reset our apps, how do we get them back?
like they're all gone.
Yeah,
How do you get all your apps?
I don't know. All that's left is finance.
Because every time you tell us to erase the
I think if you
Yeah.
just, if you go to memory, if you go to second mem and you reset it, it should do like factory reset, which should have them all back in there. I don't know how else to do it. Anyway, guys, the inequality thing is okay. I just think it's kind of annoying personally, but either way. That's how you use your graphing calculator to get a basic system of inequalities, or I should say inequality. Because this is just one inequality, right, guys? Right? So the title says system. What does that mean?
multiple.
What if there's multiple ones? Now, check it out real fast. Don't be robots. Check it out real fast. You might not need to write all this. System of inequalities, you have more than one. A solution is a point that works in all of the inequalities. And in order to work in all the inequalities, it better be in the here's my way of always saying it. It's in the overlap. What do I mean by that? Yeah, if you're gonna have multiple shadings, those multiple shadings have an overlapped region, and an overlapped region consists of points, and those points will be the solutions. Just because a point is in one of the shadings for one of the inequalities does not mean it's a system, or a solution, I should say, of the entire system. You guys are kind of used to that, hopefully. That's in the somewhat recent past. Shading multiple inequalities, finding the overlap, and then knowing whether or not a point is in that region. So, sketch each inequality separately. Find the region in common, the solution set, which is the same thing as what I would call the overlap. My artistic ones, you can have fun with multiple colors. However, one quick new thing that we should talk about. The vertices of a solution region, you can think of them as the corners of a solution region. They're the corners, the vertices are the corners, kind of like a triangle, but these shapes won't all be triangles. The overlap region can be different shapes, of course. Find the vertices of the solution region, and how do we find that? They're going to be found by vertices occur at the intersections between the inequalities. The intersections between the inequalities. And how do we find the intersections? Well, we basically set them equal to each other. And say, okay, where is your shared point? Not just of your shading, but of your actual boundary line. The boundary line is the graph that we graph first, solid or dotted before the shading. So the intersections between the inequalities specifically on their boundary lines. Now, if you're using your graphing calculator, you can use what feature? Yeah, you can use the intersection feature to find your vertices. Just carefully find intersections between the appropriate pieces. I know the air turned on. Hang in there. However, if you're doing it by hand, you're going to actually have to solve for intersections. Those are the solutions. That's when you set the different inequalities equal. Most of you guys have finished writing from what I can tell. So let's go ahead and just check out one. If you guys notice, one, picture of, oh hey, hopefully we're right, and then we're done. Told you. Sketch the graph and label the vertices. Let me go ahead and make this guy bigger. And quick heads up, can your graph for graph x greater than or negative 2? Nope. You can graph x equals? That's lame.
Yeah, look, right.
Whoa.
Oh, yeah, you just put
Okay, you can cheat. Routine.
Wait, Tyler, how do you do that?
Wait, pause. We
Same,
can look at our
guys.
calculator tomorrow. Anyway, coming back. This might be a calculator, non-calculator part. How do we graph?
You just do the same thing.
Same thing you've always done, meaning let's go ahead and take this guy and let's see him as a line instead of a x minus y is greater than 2. Can't we see him also as y is greater than x minus 2? Wait, what? How did I do that? Oh, algebra, of course. I added y, I subtracted 2, and I subtracted 2. Right? Rearrange, get y by itself. At least we can say that the graphing calculator can't graph x minus y is less than 2. You do have to get y by itself. These ones are already, the variables are by themselves, x greater than negative 2, y less than or equal to 3. Just to make things a little bit clearer, let's just make this guy a blue, let's make this guy a green, and let's make this guy I don't even know what, something else.
Your truths.
Okay. So if I was to go ahead and graph the blue, we need to make our y-intercept at negative 2, right guys? So minus 2, up 1 over 1. Slope is 1, right? Rise over run. Why am I going to do dotted instead of solid?
It's not equal to the line.
Yep, it's not equal to. Why am I shading above?
Because it's greater than.
Exactly. Blue one down, green one, go. X greater than negative 2. This is one of the most commonly missed algebra ideas. It's a special line, but is it vertical or horizontal? My hint,
Vertical.
on the x-axis, go to the negative 2 tick mark and say, hey, keep going. You see me at the negative 2 tick mark? Go to the negative 2 tick mark and then say, keep going. It's a vertical line. Shading gets a little tricky. Put x greater than negative 2. Think of the x's on this side. 0, 1, 2, 3, 4. Think of the x's on this side. Negative 3, negative 4, negative 5. Which one is greater than negative 2? The right or the left? Yeah, the right. You can always test as well. Never green. Last but not least, we have our, what color is that? This one's chartreuse? I don't think so. Y is less than or equal to 3. Go to the tick mark on the y-axis, 3. Or equal to. Ooh, that's a solid line, right, guys? Where's the shading, above or below? Below. And personally, I like to go ahead and show the overlap in some other new color. That way it's very nice and distinct. And when we shade, we should be able to see our region. Now question, guys, do you see the vertices of this overlap? Do you see the vertices? What did I say the vertices were? The corners, and the corners are the intersection points. If the intersection points or the corners are the following, question, why am I making them open?
Some of them are not.
Because every single line coming into them, or every single set of lines, there's at least one dash, and if there's at least one dash, can it equal for both? No. So we have to keep them open because technically dashed lines are coming into them. And how could we solve for each? We could use the intersection feature, or we could say, hey, wait a minute, I know the x value of this line, isn't it -2? And couldn't I, for the first vertices, just call him number 1, then number 2, then number 3? Couldn't I, for number 1, say, okay, wait a minute, the x is -2, what would the y be? Well, who's the other line, guys? This one's y equals 3, so couldn't I say it's just -2, 3 without even really using my calculator? Number 2, my x value is yet again -2, but what is the other function coming into this guy?
-4.
Yeah, it's y equals x minus 2, so I plug in -2 minus 2. What's my y? -4. And then for number 3, I have my y value of 3. I just need to plug that into my y equals 3, which equals x minus 2, x equals 5. I have my 3 vertices, same thing as my 3 corners by finding my intersections. If you graph carefully, maybe you can see it on your graph. Alright, kiddos, there might be some applications in this homework, but look, we got it right. Alright, homework 7-5. Play with shading tonight, play with a couple applications. You guys are good to go. It's 9:30.